I want us to look at part C of the optimization problems, but these optimization problems are a little bit different from the optimization problems that we did in lecture 45 and lecture 46. So one of the reasons I did that was if you look at these problems, those problems are kind of specific to the field of pharmacy. If you are dealing with certain drugs, you will notice that when you're having a drug, when you're injecting a certain drug in someone's body, or when you are giving someone a certain drug and you wanted to actually manage it, there are some cases whereby you don't want the concentration of that blood of that drug to actually exceed a certain amount of concentration, or you don't want it to be too below. Either when it is too below, it's not going to be, the drug is not going to be much more effective, and also when it exceeds a certain limit, you will find out that it's actually going to be dangerous for a certain patient. So that is why I decided to add these problems. The second reason for that is because most of the time, when you are actually dealing with some of the optimization problems, you always tend to think that every time you have to take a derivative, and then after taking the derivative, set it equal to 0, and then you continue to do all those things. And if you still remember what Abraham Maslow once said, he said that if the only tool you are familiar with is a hammer, everything starts to look like a nail. So every single problem that you are facing, if you are always using a hammer, you always think that you can always fix it with a hammer. The same thing with the problems that we did in part B and also in part A. We'll always use to find the formula, use the derivative, and so forth. But that is not the only case whereby you are dealing with optimization problems. You don't always have to take a derivative. And also, my other reason was when I was waiting for this before uploading this video for this part, I wanted you to first write a test, and then after the test, that's when you can follow this, because I don't want to confuse anyone, because these most of these problems in part C are a little bit different from the other problems that we did in part A and part B. Of course, let's start with the problem number 11. As I've always said, the first thing you must always do, excuse me, copy this problem and then try to solve it, and pause the video and see what you're getting. If you're getting the same thing as me, bingo, we are fine. And then you go to question number 11, you copy it, and then you try and solve it and see if you're getting the same answer as me. And if you do, you can proceed to 13, and then you can copy it, go to 14, and then you can copy it, and then you can go to 15. You can see from 15 and 14 are very straightforward. And also, if you look at 14 and 15, they are very easy. I also added one problem number 13 so that you can also see a little bit of twist in those problems. Copy the problems and see if you are getting the same thing, and then if you are not, then you can follow through. Like I always said, these lessons are not about number of viewers or anything of that type, where the hours are like that and all those things. What is important, I want you to be exposed to information. So if at least you understand this, I'm happy, because I know that maybe next year, if you happen to get good marks, you will be tutoring other kids. And when you're tutoring these kids, you will make sure that you are giving them the proper information, and of course you also get good marks for yourself. So that is one of the reasons why we are trying to store some information for our future leaders. So let's start with number 11. Already wasted about 5 minutes. On this, it says a drug concentration in the bloodstream after a dose is given by this equation here, where D is the initial dose, K is the elimination constant, T is the time in hours. So when you are injecting one dose to a patient, every single time you inject a dose, it is characterized by this equation, and this D here is the amount of dose. If let's say the dose that you have in your needle, let's say is 5 milliliter, that is what this D stands for. And this K here, it is actually the rate at which the drug in the body metabolizes, or it leaves the body. That is actually this K here. Then the question here is saying, find the time T that maximizes the concentration if a second dose is administered at time T. So suppose you inject the first dose in a patient, and then after injecting this dose, you find out that, okay, it starts decreasing, or it starts metabolizes in the blood, and then you want to look for the best time T so that you can inject the second dose. And then when you are injecting the second dose, you want to make sure that you get the maximum total concentration of these two doses. Now, what will be the time T so that you can get the maximum concentration? Let me explain here what is actually going on. So, of course, we are in question number 11. So, basically, you have your concentration with respect to time as D times E minus KT, which means now if T is equal to 0, so if let's say T is equal to 0, C of 0 is equal to D, and then you have E raised to minus K times T, which is 0. So K times 0, you know that it's actually going to be just a 0. And then E to the power 0, you know what you are actually going to get. You will end up getting E raised to power 0, you will get a 1. So this whole thing is going to be 1. In other words, the initial dose is equal to D. Okay, now that's what we know here. Just the moment you injecting that dose, the amount of concentration in the blood of this dose is going to be just D, and then as T keeps increases, then it starts to decrease down. Let's suppose that you inject the first dose, so only for the first dose. What is the graph is going to look like? The graph of the concentration versus time. So suppose we are having a graph here. I'm gonna make my graph look nicer so that you can see what we are actually doing here. Well, let me remove the ruler. This side in the y-axis will have the concentration. Along the x-axis we will have time. So the moment at T is equal to 0, the moment you just injected the dose, you will find out that at this the dose is going to be D. That's the moment you just injected the dose. So the concentration is just gonna be a D there. It's going to be the whole dose. It's not going to be reduced or increased. It's going to be there. And then because you know that whenever you are having this function here, you have E raised to minus, if let's say we're having some T here, some T, you would find out that the graph is actually, let's say we're having a graph, the graph is supposed to increase like this, right? The next thing that you do, once you are placing a K there, all you are actually doing here, you are actually stretching this curve horizontally, so you still get something of this type. So even if we're having a K there, as long as this K is positive, when you are having now E raised to minus a KT, so having this minus here, you know that it is a reflection about the y-axis. So the graph is supposed to look something like this when you are having a minus there. So which means now if we are starting at this particular point, this curve after the first dose is supposed to look smooth, and then it goes down just like an exponential function. So it's supposed to just keep going down, keep going down, keep going down, keep going down, keep going down. And if you look carefully in this, it's not going to touch these t-axis here. And this one here is only the first dose. So this one is the first dose only. So when we are having the first dose. Now, if let's say now we inject the second dose. Suppose we inject the second dose. I am going to assume that the time t is supposed to be here. I'm making a general assumption here. I want you to see what I'm doing here. And then once you inject at this time here, you know that at that moment when you are injecting a dose, it's supposed to be a d here. Remember that we're adding a dose based, we're injecting the dose at this time here. If let's say this dose here, we did not have this dose, this dose was supposed to be here, so we're supposed to have a d somewhere there. Let me repeat what I said. If we were only having the second dose, this one we did not have this first dose, the dose was supposed to be at d, at this value d here. But now I am injecting the second dose while the other dose is still in the blood, and it is this value. So the difference from this horizontal axis to this point is going to be the difference from this point to that point. So actually, once I add the second dose will actually create a concentration that is going to be somewhere there, and then it starts decreasing smoothly. So you can see here at this point that you will have the first concentration of the first dose, which is T, and then plus the second dose, which is just gonna be D, because I have just injected it at this point. And then as you are going further, this whole thing, it starts decreasing and it keeps going down, it keeps going down, and there's no other reason that is actually going to be different. This is gonna go down forever. What I want you to realize here is that this dose alone, once I add the second dose, is going to be a little bit above, because this second dose is added from the concentration that is already there. So we'll get a value that is up there a little bit. Now, the second thing that I want to realize here is that if you look at this point here, this point here is actually below this point here. So if I were to add this dose, it was going to be somewhere above this point and above that point. So as much as I keep picking points that are actually before that, I get a value above. Of course, when I'm adding this D here, in other words, when I'm injecting the second dose, it's actually gonna get a value that is a little bit above there. And if I pick a value here, this value is above that value. So whenever I'm injecting a dose somewhere at this point, the concentration is actually going to be a little bit up there. And if you keep noticing here, the more I keep picking points that are below these points, I actually get a bigger concentration than this one. What does that mean? If I were to inject this first dose and the second dose at the same time, I will get a value that is, let's say this is 1 2 3 4 1 2 3 4. I will get a value that is somewhere there. So I take the two doses at the same time, and then I add them, so that the initial dose is just 2D at that particular point. you can see that that's the only point we are actually getting the maximum concentration. In other words, that's the only time we are getting the largest concentration. If I were to add this and also add the second dose at the same time, I'll get a value there. The moment I keep waiting, then at that point the concentration will be there. So when I'm adding the second dose, I will get a concentration that is way below there. So the largest concentration I should get is when I am actually adding both the two doses at time is equal to 0. T is equal to 0. So here, find the time that is best, so that when you're adding the second dose, we're actually getting the maximum total concentration. So that is what this question was saying. In other words, what we are looking for here, the solution to this question, T is equal to 0. That's what we're looking for. This thing looks complicated because I was trying to explain that if you add both these two doses, you will end up having 2D, and then it's gonna go down smoothly. But this one is the only point we are getting the maximum concentration. But if you decide to pick some other time, the value of the concentration you'll get is a little bit smaller. So that is what is important with question number 11. Let's go to question number 12 and see if there is any difference that we can actually get. A drug must be maintained in the bloodstream above a minimum concentration for 24 hours. The concentration at time t after a single dose is given by that, where D is the dose, V is the volume of distribution, K is elimination rate constant. What dose D minimizes the total drug administered over the day if doses are given every 6 hours? I want us to read this question because myself either I don't really get it for the first time, so I usually read it for the second time. A drug must be maintained in the blood above a minimum concentration. So let's just interpret what is happening before this dot. You have a drug that you want to inject in a patient, and you want to make sure that every time you check the concentration of this drug, it must always be above a certain concentration, because if it is less than this concentration, the drug is not going to be effective to make the patient heal from whatever disease or from whatever problem or whatever health issue this patient is having. So you want to make sure that the concentration is always above that. That's point number 1. The second point is saying that the moment you place or you inject a dose in a patient, it is always going to be characterized. The concentration can always be modeled by this concentration, whereby this D is the amount that you are injecting, is the amount that is in the needle that you are about to inject to the patient, and also this V is actually the what do you call it? If we're saying this is a volume of distribution, it's the area that is actually going to be affected by this particular drug. That's how I usually look into it. And then this K here, of course, is the rate at how fast this drug leaves the body, or how fast your body is actually metabolizing this drug. That is actually this K. And then, of course, E, we know it is the Euler number. So that's what we're actually having here. And then let's look at the question. What dose minimizes the total drug administered over the day? So because we will be, what dose D minimizes the total drug administered over the day if doses are given every 6 hours? So what we are trying to do here, every 6 hours we keep injecting this amount of dose, right? And then every time we're injecting this fixed amount of dose every 6 hours, or there is this pill that you keep taking after every 6 hours, we want to find out how much of the dose should we give so that this the concentration is always going to be above the minimum concentration, and also at the same time we want this dose to be the smallest as possible. One reason why you would want the dose to be smallest as possible is because you want to minimize the cost of buying this medication, and also secondly, one reason why you would want to minimize this, you don't want to end up giving an overdose. That's also another reason. So we want to minimize this as possible so that we don't end up running out of meds because of we're overdoing this, but at the same time want to be above a certain concentration minimum. That so let me first write what is happening here. So every time I'm injecting a dose, I know that I'm supposed to get dk divided by v times e raised to minus kt. That is actually the concentration after each dose. So that is that. I'm just looking into it. Now, if let's say I wanted to model what is basically happening here. If let's say, remember that after every 6 hours, let me draw this. Maybe it's going to make a lot of sense if I draw it. Suppose I draw this, and then I get this nice thing here. And then this side, of course, I want concentration to be this side, and then this side I want time to be there. And then of course I want to first, after every 6 hours, and I want to model this for 24 hours. This is the first 6 hours window, and then this one is the second 6 hours, and then this one here is also another 6 hours, and then this one here is also another 6 hours. I'm trying here, this is not perfect. I know that here we have 0, and then here we have 6 hours. Here we have the reason I'm doing this, I want to make sure that my curve looks fair. So we have 6, we have 12, we have 18, and then we have 24. So we keep injecting a dose after every 6 hours, and then we want to manage what is going to happen after every 6 hours. And then the next thing that I'm going to do here, I wanted these to be dotted lines. Of course, these are dotted lines, and then here these are dotted lines. These ones are dotted lines, and then here these are dotted lines also. So what we want here, we want to make sure that let me put this one here. I want this to be blackish. Okay, I'm gonna do this. Okay, and then after that I'm gonna make sure that this is also dotted lines. These are also dotted lines. I want to explain what is happening here without causing any confusion. So what is this statement saying in question number 12 is that I have a dose after every 6 hours, that is fine, and I want to make sure that the concentration is always above the minimum concentration. So this one here is this one is C. This one is going to be the minimum concentration, or C-min. So when I first inject the first dose, I know for a fact that the first dose is going to be somewhere there. And this point here, when t is equal to 0, this is going to be 0. 0 times k, whatever the value of k, this is going to be 0. And of course, e to the power 0 will end up having a 1. So the initial concentration is going to be that. So we'll end up having d k somewhere there divided by a v. That's going to be the initial concentration once we inject the dose initially. And then from there, we know that we wanted this, because this is an initial, we want it to be above, but we have a minus there, which means this will start decreasing. Whether we like it or not, it will start decreasing. So we don't know how decreasing it is, but we want to make sure that it is always above. And then, of course, because we are here, and then at this point here, this just before, we want to make sure that it is above or it is equal. And then just before I inject the second dose, I injected the second dose. It was supposed to be here if the first dose was 0, but now the first dose must always be above this, which means that once I add the second dose, I have to add this difference from this point to that point. So it's going to be a little bit above here, and it's going to be somewhere there. I'm just going to suppose it's somewhere there. This is not 100% because we don't even show that this is going to be exact here. It might be a little bit above or there, but we'll have this smooth decrease here. And of course, the second is going to be there after the second dose. And then, of course, it will gradually keep decreasing, 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 and decreasing and decreasing. Maybe it's somewhere there just before I add the third dose. But once I add the third dose, I know for a fact that once I add the third dose, it's supposed to be somewhere there, somewhere a little bit above there, and then it gradually keeps decreasing, and it keeps decreasing, and it keeps decreasing, and it keeps decreasing. Once it arrives at that point, maybe a little bit above, I add another dose, and once I add another dose, it's going to be a little bit above there, and then once I inject it, it starts decreasing, 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 and then we enter there. And then, of course, after the 24 hours, I'm supposed to add another dose. But the question is saying here, we want to administer, or the drug must be maintained for 24 hours. So we're supposed to stop there. This is just the sketch of how this scenario that is explained here can actually happen, because every time you inject the dose, you inject it, and then the concentration keeps dying down because the body is actually metabolizing that medication or that drug. So that is actually what we are getting here. We want to actually end up analyzing now what is basically happening. This one here, I'm going to use a blue. This one here is first dose only. So the first dose only is characterized here by this single thing here. So we wanted to talk about total concentration. Total concentration. So we want to talk about the total concentration. Now, if we talk about just before the second dose, C total, or the total concentration at just before the second dose, just before the second dose, I'm going to put a 6 there. I want us to see something here which is very much interesting more than anything else. The reason I'm looking at 6 is because once we take this point here, we know here we're getting a max, but as this one keeps decreasing and decreasing, the only way we cannot satisfy this condition that the concentration must be above C mean is when we are close to the second dose, because this keep decreasing. So we wanted to make sure that just before the second dose we actually get the concentration, and we'll make sure that just before the second dose this concentration is above this C mean. So just before the second dose, we'll end up having D of K divided by V times E raised to minus K, and then our T is going to be 6. And of course, we are having this dk divided by V E raised to minus 6K. That is what we're having. This is the total concentration that we're having. The condition here is saying the drug, okay, what is saying? What dose D, if dose is, what dose D minimizes the total drug. So wanted to actually minimize the total drug in the body. In other words, we also want to make sure that the concentration is above where's this? Is above this C mean there. So we are having this one here. Take note that before the second dose, which will happen at this point, this is actually going to be the total concentration that we are having. And of course, we want to make sure that C total at 6 must always be bigger than or equal to C mean, which is the minimum concentration at that time. And of course, we are having our dk divided by V E raised to minus 6K. This one want to make sure that it is way above C mean. And then of course, if I'm solving for D here, I want to make sure that my D is going to be greater than or equal to, I'm going to cross multiply, so I will end up having V times C mean. Let me rewrite this a little bit down. So we are actually going to end up having our D is greater than or equal to, I'm going to cross multiply. Remember, there is a 1 there, and this E here is actually in the numerator if I'm having it the way that I was having. So I'm going to cross multiply there. I will have a V, and then I will have C mean, and then I will divide by K E raised to minus 6K. So that is actually what we are having. So our D must be bigger than or equal to that, so that the concentration at this point is actually above. So because, let me write this one here, because we want to minimize the total drug, what was this saying? Let me look here. Total drug administered, we must have our D not bigger but equal to V times C mean all over K E raised to minus 6K. That is actually the first condition for only dose number 1, or the first dose here. If let's say now we are talking about the second dose, second dose. So when we are dealing with the second dose, bear in mind that I'm going to use the same rate. This one was supposed to continue. This one, it was supposed to continue all the way. This one is going to continue to decrease all the way, but it's not going to actually reach this one. And then of course this one was supposed to actually continue to go down go down all the way, and this one was supposed to actually continue all the way down, and then it keep the same thing. This one was supposed to actually keep continuing, but we only know the information just before 24 hours, so we are not having that at all. Now let us look at this concentration, because before we actually get to this concentration here, I want us to realize that we added the concentration that is actually concerning the second dose, and also the concentration of the first dose, because it kept continuing. That's why we ended up getting this bigger curve here. Now let's look at what will actually be the concentration just before I add the third dose. So what will be the concentration at that particular point? So if you look at this concentration for this one here, this one is going to go all the way. So I'm still having the concentration of the first. Let me first write this one here. Now for the second, or let me write it like this so that it's not confusing. I want to write it like I wrote it here. This one I was just focusing the total concentration just before the second dose, so I want to talk about just before the third, just before the third dose. So before the third dose, I want you to note that we have the first and second dose. That is our C total at 12 now is going to be equal to this. So when we are at this moment here, just before we add the third dose, we have to check what will be the dose for this one here. So if you look at the concentration, not the dose, make a mistake. If you look at the concentration of the first dose, it's going to be somewhere there, and we are going to look at it separately for this part here. So we'll end up having the concentration of the first dose at T12 plus the concentration of the second dose. But now if you look at the second dose here, it started at 6 and then it went all the way up until it arrived here. So for the second dose, the time it took from moving at 6 hours to 12 hours, what is going to be that difference? So here you will be having T equal to 12 minus 6, which is just the same as a 6. I don't want you to end up getting confused. Where did we get this 6? It comes from that difference. And if we are using our equation here, this one is supposed to be dk over v, and then we have e raised to minus k, but instead of t we have a 12, and then plus, and then for this one we will end up having we still have this dk over v, e raised to minus k, but now we'll have a 6. So this whole thing is going to be d. We'll end up having a k for both of these two things, and then we'll end up having a v, and then inside here, because this and that is there, I will have e raised to minus 12k and then plus e raised to minus 6k. But if you look into this one must always be, we know that since C total, the total concentration, we want to make sure that it is above or equal to C mean, right? So what we want our dk divided by v, and then inside I have e raised to minus 12k plus e raised to minus 6k. We want this to be bigger or equal to C mean. And then if you continue with this one to solve for this one is in the denominator, so we multiply. This means that we must have this bigger than or equal to V times C mean. And then because this one is actually, these ones are actually in the numerator, so they go to the denominator, so we'll end up having K times E raised to minus 12K plus E raised to minus 6K. So we are actually having our D must be bigger than that. I cross multiply it here because we have a 1, so I cross multiply it by that. Since D must be a mean, I can just say therefore D, I want my D to be actually equal to VC mean all over K into E minus 12K plus E raised to minus 6K. So remember that we are looking for the total, want to minimize the total dose that is actually being affected here. The next thing that we wanted to do here, if let's say now we actually, because we dealt with this position, now we add this dose, we want to find out that what is actually the concentration at that point, just before we add the fourth dose, what will be the concentration at that point. So if you look at the concentration, of course you will notice that actually C total just before the third dose. Okay, this one was just before the second dose, this one just before the third dose, just before, not the third, the fourth. Here we're at the fourth, just before the fourth dose, which is we dealt with this point, we dealt with that point, now we are dealing with that point there. What is actually going to happen there? So before the fourth dose, before the fourth dose being injected, what is actually happening? I'm just going to do this and then I'm not going to continue. I'm going to explain what is going to happen here. So the total concentration at 18, T is equal to 18 just before the fourth. So we're having that. So we'll end up having the contribution of the first dose, right, is going to have 18 hours plus the contribution of the second dose. What time will it take? Plus the contribution of the third dose. So those are the doses that we're looking for. So if let's say I am here at this point, you must know that this one moved from 12 to 18, this third dose. So this one here after the third dose. So you can see that this one here is actually going to take from this point to that point, which is 18 minus 12, 6. So that's the time it's going to take. So it's actually taking 6 hours. So we'll end up having here T is equal to, so we'll have a 6 here. And of course, when it comes to the second dose, this second dose here is going to move from here at 6, and then it goes all the way until it arrives 18. So the hours between 6 and 18 is going to be 18 minus 6, which is equal to a 12. So we'll end up having a 12 here. So when you look into this here, this is just going to be dk divided by v e raised to minus 18k, plus this one is going to be dk divided by v and then e raised to minus 12k, and then this one is going to be dk divided by v, and then we have e raised to minus 6k. So That is actually what we are having here, right? So after having this thing here, we will actually end up having a decay. I'm going to actually factorize this thing here because it is the same everywhere. And then inside here, we'll end up having e raised to minus 18k, and then plus e raised to minus 12k, and then plus e raised to minus 6k. That is actually what we end up having as the C total after 18. But another thing that I want you to realize is that C total, this one must always be bigger or equal to C mean, right? Which means that our dk divided by V and E raised to minus 18k plus E raised to minus 12k plus E raised to minus 6k, this one must always be bigger or equal to C mean. I've just substituted this, which is that. And of course, if I'm solving for D here, I will end up having D must be bigger than V times C mean, and then divided by K times E raised to minus 18k plus E raised to minus 12k plus E raised to minus 6k. Because we are looking for the minimum, let me use a red here. Because we are looking for the minimum total drag, we want our D to be small. So this one is bigger than that. So the smallest value we can have is when this is equal to that. That is why we choose our D to be equal to V times C mean. This is supposed to be C mean all over K, and then we have E, and then we have minus 18k plus E raised to minus 12k plus E raised to minus 6k. And then of course, if let's say now I'm just gonna do a shortcut here, just before the fifth dose, you will see that the C total, if you continue in the same scenario here, you will end up having C total being equal to dk divided by V. Of course, you will end up having here E raised to minus 24k plus, this is a 4, plus E raised to minus 18k plus E raised to minus 12k plus E raised to minus 6k. So you'll end up having something like that. And then of course you will end up having your D being bigger than or equal to V times C mean, and then this whole thing divided by K times E raised to minus 24k plus E raised to minus 18k plus E raised to minus 12k plus E raised to minus 6k. So you'll end up having that, and then you will be choosing your D to be equal to V. You will end up having V equal to V C mean, and then you divide this by K, and you have E raised to minus 24k plus E raised to minus 18k plus E raised to minus 12k plus E raised to minus 6k. So you'll end up having something of that type. But now, what I want you to realize here is this nice thing here, that when you look at these values here, let's go to the graph again. When you go to the graph here, and then you remove this connection here, I will tell you why. Suppose that we are only focusing on the initial graph we had here. If you look at the smallest value that have a risk of becoming less than this minimum value, is when we are at this point here. This point is going to be above that point. That point is going to be above that point. That point is always going to be above at that point. So the only value that we should be focusing on D, I mean the value that we should be focusing on when it comes to actually D is actually the value associated with the first dose, because the first dose is the only dose that have a risk of actually getting a value that is actually smaller than this C here. All these other values will always be above this line. This one is the only one that have a risk. So if we can make our drug our dose to be this dose here, I think we will actually end up having a minimum dose that is actually going to actually make sure that we are always above this point. Why am I saying so? It's because when it comes to this one here, where's the second one? When it comes to this dose here, this dose, this value here, comparing this one, let's say we're going to write these only. Comparing this these values, let me just write them here. So we are having our D. One of our D is saying we are having V times C mean divided by K times E raised to minus 6K. The second one is saying our D must be equal to V, and then we have C mean, and then we divide this by K times E raised to minus 6K plus E raised to minus 12K. And then the next one here is actually saying our D must be equal to V, and we have C mean, and then we divide this by K, and we are having E raised to minus 6K plus E raised to minus 12K, and then we are having E raised to minus 18K, and then the last one is actually having D is equal to V, and then we are having C mean, and then we divide this whole thing by K, and then we have E raised to minus 6K plus E raised to minus 12K plus E raised to minus 18K plus E raised to minus 24K. So we are having these values here. So the next thing that we want to make sure of is this. When it comes to this value here, when we are looking at these values, you will find out that this value over here, because this, let's look at this value in the numerator, and that and that and that is the same, but this value in the denominator here, this one here is actually smaller than that, and actually this one is actually smaller than that, and also this one is actually smaller than that. So this one is smaller, which means this value is bigger. So the inequality is actually going this way here, because this one is smaller, therefore this whole thing is going to be bigger. So what we are actually getting here, we are getting the inequality going like that. So we are actually going this way, and of course we are going this way. So this D is bigger than this one, and this one is bigger than that one, and this one is actually bigger than that one. So the question that we're actually having here is this. We are saying that we wanted to make sure that at each point in time, the dose is actually, the concentration is actually bigger than the initial, it's actually bigger than this point over here. So whatever the value that I actually pick at this particular point here, I want to make sure that it's going to be above this initial point. So the first concentration, we want to make sure that D is actually bigger than that. D must be bigger than this for the first concentration. So once this one is actually satisfied, which means if this one is actually satisfied, then all the others will be satisfied according to this equation here. All of them will actually be satisfied. So once we have our D equal to this this point here, we are actually fine. So that is the most important thing that we want to actually end up having here. So once this one is satisfied, this problem is kind of confusing to most people, because what they want to do here, because this is bigger than that, this one is bigger than that, and this one is bigger than that, and we are actually looking for the smallest D. They want to end up choosing this one here and say that our smallest D should be this thing here. So if we are having our D equal to this thing, then we are sorted. But if you are choosing this whole thing, you're not gonna satisfy this one. As much as we are dealing with the smallest value here, we have to choose this one, because this one, once it's satisfied, all the others will be satisfied. But once we choose this one here, we will have a problem, because this one will not be satisfied. So what we can actually say here, the conclusion here is saying, I can say this, the conclusion, if okay, the conclusion, the D we are looking for is D equal to we have V times C min divided by KE raised to minus 6K. So that is actually the D we are looking for in this particular case. I hope I have answered your question, that as much as the inequalities are going this way, we want to make sure that this one is satisfied. So once this one is satisfied, all the others will be satisfied. That is why the D we're looking for is this one, not the other ones that we've been doing. Let's go to number 13. So we are at number 13 here. Number 13. So we have a 13 here. What is number 13 saying? Number 13 is saying a pharmacist is formulating a capsule that contains two active ingredients, ingredient A and ingredient B. The cost per mg for milligrams of A is this and B is that. To be effective, the capsule must contain at least 100 mg of A and at least 150 mg of B, and the total capsule weight must not exceed 300 mg. So this one is actually very important. How much of each ingredient should be used to minimize the cost? I want you to make sure you know what you are actually minimizing here, because once you don't know, you will start to have a big problem. So the first thing that is actually being said in this problem, we want to form a capsule. Let me put it like this so that we end up not confusing things. We want to actually create or you want to form a pill. So we have a certain disease that requires us to have this pill. So I want us to actually form this pill. So this pill must have, so we can say that they're saying that you have two must contain. So let's say, let's create some notation here. X is going to be, let me do it like this. Let X be an amount in the capsule, the amount of A in the capsule. Okay, and then Y be an amount of B in the capsule. That's what we want, capsule. And then the next thing that we want to find here, we have this. The cost per mg of A is 0. So the total cost, I'm gonna say that C, I'm going to say here C of, let me just say C of C, the total cost, the total costs. Okay, so we have X, Y, and C, the total cost. So they are already telling us that C is actually going to be the same as 0.03 X, because it contains of A, plus, and then 0.07 times Y. The question, the statement is saying the cost of A is $0.03 and cost for B is 0. So if I know the amount, this one is the amount in A, I would just have to multiply by this, because for each MB we have this costs, and also for each MB in B we have this cost, so I just have to multiply by that. So this is the costs, the total costs. Okay, the total costs, let's say per capsule, right? So we have this total cost. The second statement is, to be effective, the capsule must contain at least 100 MB of A. So what this thing is saying we want to have X, and our X, we want it to be bigger or equal, at least means bigger, 100, and then of A, and at least 150 of MB in B. So we also want our Y to be bigger or equal to 150. Okay, and the total capsule weight must not exceed 300. So if I'm adding X plus Y, this one must always be less than or equal to a 300. So those are the conditions that we are actually having when it comes to this. So how do we solve this problem, only given these constraints here? All you need to do here, first realize before this thing here, this one here is actually telling us that we want our Y to be less than or equal to, this was 300, less than or equal to 300 minus X, or simply put, our Y is less than or equal to minus X plus 300. Okay. One thing that we can actually do here to actually end up making our life easy, let's first draw and see what this statement is actually telling us here. Because once we draw these statements, we will be happy. And then I have 100, I have 200, I have 300. Let me move forth. I have 400. So that is actually what is happening here. I have 100, I have, this is 100, I have 200, I have 300, I have 400. The same thing here, minus, 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 minus. Okay. So the next thing that we wanted to find out here, this side we have Y, this side we have X. So we want our X to be bigger than 100. So X is bigger than 100 here. So we want our X to be somewhere there. I'm gonna draw a straight line at 100 because this is 100, and then I know what I'm looking for, that my X, I want it to go to be only this side. So we have this side, so X is only in this side because we have bigger. And then the next thing is saying we have Y, our y, we want it to be above 150. This is 100, so our 150 is somewhere there. So I'm going to draw something here. It's somewhere there. Of course, this is not 100% correct. So our y is actually this side because it's above 150. And then when I'm adding x and y, we have this, or I have y is equal to that. So if you look into this, if let's say here I am actually having x equal to 0, I have to go to 300. If x is equal to 0 somewhere there, 1, 2, 3, so I'm supposed to be somewhere there, 300. Okay. We have that one here. In this equation, if we are having x equal to 0, we'll have that. I want to draw this line and then talk about it. And then the next thing that I want us to do here is this. If I set y equal to 0, I will have 0 here, and then take this x will be positive this side. So x is also a 300. So I have 1, 2, 3. So I am sitting here. So the next thing that I want to do, I want to draw a line that is passing through these nice points here, because this is not drawn to scale. And if I am looking for the side that I'm looking for, I'm looking for the side. Remember that I'm going that side. This one here is saying look for anything that is going that side, and then this one here is saying look for anything that is going up. So I'm looking for going up. So this one is up, this one is going up, but this one want anything that is actually below this line. So below, so I'm looking for below. So what this thing is actually saying to us is actually telling us that look for the values that are actually in between here. And then the values that are actually giving you the maximum or the minimum cost. What is this question saying? How much will minimize? That will give you the smallest of this value are the values that you are looking for. So how can you actually conquer that? So first thing, we look for this one, we look for that, and then we look for that. So we have this point, and that point. So we have those 3 points. So what you do, you just check this point and that point and that point, which combination is giving you the smallest value there is there. That's how you solve this question. So what is that point? This point here, we're having 100. So we have x. Remember that we have x and then y. So here our x is just 100. So we have 100x. And what is actually y at this point? The y that is associated with that point is actually going to be on this line here. So if I'm plugging in 100 here, this is going to be 200. So I'll have a 200 there. And then the second thing, what is that point? You can see that our y at this point is actually going to be at this point here. Our y is actually going to be this here, which is actually 150. So we have a 150 here. And then if this one is 150, and then I'm taking this here and then subtract, this one is also going to be a 150. Because I'm going to plug it in this equation to get the x, because the x is there. And then when we go to this one here, our x is going to be, we have x is going to be 100 and y is going to be a 150. That is what is important. So you plug these 2 values in the costs, plug these values in the costs, plug these values, and the value that is smallest is going to be the minimum. So what we are getting here, the cost equation, it has x and y, of course. So it's 0.03 x plus 0.07 y. So if x is equal to 100 and y is equal to 200, what is going to be the cost? So C of 100 and 200 is going to be equal to 0.03 100 plus 0.07 200. And without a calculator you can solve this, because 100 is saying move this thing 2 times, so you'll end up having a 3 here. And then when it comes to this one here, is saying move the comma 2 times, 1 2, 7 times 2, this is going to be 14. Because 200 is the same as 2 times 100, and then multiplying a number by 100 is just moving this comma 2 times, so we move it here and there, we get a 7, and then 7 times 2 is a 14, so this one is supposed to be a 17. Let's look at C of 150 and 150. So we're having here x is 150 and then y is 150. So how do we deal with that? We will have 0.03 and then times 150, and then plus 0.07 times 150. And if you look into this one here, you will find out that how can we actually deal with 150? 150 is the same as 1,5 times 100, and 1,5, I'm going to change this one here. I will have this one is going to be 0.03. I will have 100 times 1,5, because I will move this twice and have 150, 1,5, and then of course 1,5 is the same as 3 over 2. The same thing here, I have 0.07, and then I will have 100 times 3 over 2. And if you look carefully into this one times 100, I will end up having a 3 times 3, I will have a 9 over 2 plus, and then here I will have 7 times 3, I will have a 21 over 2. Hopefully my maths is right here. I have a 2 here, 9 plus 21, that's a 30. That's a 30. And then we'll end up having a 15 here. Of course, this is not just 15 dogs. We were using dollars, so it's supposed to be $15 and also $15 here. And then the next thing here, we want to see C of 100 and 150. So we have x is equal to 100 and y is 150. Of course, we have 0.03 times 100, which is just a 3, plus 0.07 times 150, which is just 100, times 3 over 2. Is it true that 100 times 3 over 2? Don't want to make mistakes here. Okay, that's fine. And then this one here, move a comma 2 times, 1 2, so we'll end up having 3 here, and then plus, and then here we have 7 times that, we have 21 over 2. So that is what is important. 7 times 3 is 21 over 2, and then 3 is the same as 6 over 2. Of course, 6 plus 21, that is actually 27 over 2, because the common factor is a 2. And then how many 2's out of 2? We have 1, and then there is no remainder. How many 2's out of 7? We are actually having a 3, and there is a remainder, which is 1. And then how many 2's out of 10? We have a 5 there. So looking at this number here, and at that number there, and at that number there, this is actually the smallest dollar. So we've minimized this amount there, which means that what we're supposed to end up having, x must be equal to 100, and then y must actually be equal to 150. So this is actually what you need to understand when it comes to minimization of these problems here. Another thing that I wanted to specify here, not every time you end up having to take a derivative. You can see here in question number 11 and question number 12, we did not take a derivative at all. And now at 13, we actually did not take a derivative at all. What we just realized that there are this bunch of inequalities that are actually telling us that whatever these values should be, they should be in between these points here. So everything need to be satisfied, so they need to be inside here. And whenever we're checking things that are here and want to minimize or maximize the problem, we just check these endpoints here, or these vertices that are here, and then we check them in this equation. And then once you check them, you're actually gonna be sorted when we are dealing with these inequalities there. And then the next thing here, the next thing that I want you to actually realize now is that we are having question number 14, and of course question number 14 and 15, they are very straightforward. It's only those questions that I wanted to just introduce them so that you can see that there are questions, minimization problems, especially when it comes to operation research, that there are these questions here. But now we have 14. A 14 is saying a patient requires an IV drug to reach a therapeutic level as quickly as possible without exceeding a maximum safe concentration. The concentration in blood is given by this, where R is the infusion rate, V is the volume of distribution, K is the elimination constant. What infusion rate R maximizes the rate of increase in concentration while staying below a safe threshold? So we are having this question here. This one is not that hard, it's straightforward. And then 14, a pharmaceutical company wants to package pills in a cylindrical container. Each pill has a volume of 0.4 centimeter cube and the container must hold 100 pills. Question: what dimensions, radius and height of the cylinder container will actually maximize the package, the amount, minimize the amount of packaging material? So I want us to start with 14. 14 is straightforward, but just take I hope you can see the difference between these questions, because these questions are not one. That is why I wanted most of you to first write the test before doing this, because when you're looking at these questions, they start to confuse you, because it's no longer all about taking derivatives. Sometimes you take, sometimes you don't. And if, let's say, you were to force to take a derivative here, what was going to happen? You were going to end up having to interpret a lot, especially with number 11, number 12. And also here, this was going to actually make things harder for you if you don't draw. And let's look at number 14. What would happen if we don't? Number 14 also, you can just analyze what is going on here and solve it without taking much about derivatives. But I want us to take derivatives here so that we're doing something that is also familiar with what you did before, where R is the infusion rate and V is the distribution. The question is saying what infusion rate R maximizes the rate of increase. So the rate of increase, what are we trying to maximize here? We are given this concentration here. There are no intervals, there is nothing. So we're only given this and there is nothing else that is given. So let us go back to the drawing board. Where's number 14? Okay, I'm gonna write here number 14. So we are having our concentration, and this concentration is given by R divided by K times V, and then we are having 1 minus E raised to minus KT. That is what we are having. Now let's first talk about the rate of increase. What is the rate of increase of the concentration? To describe the rate of increase, let's talk about we want to actually maximize the rate of increase. how much is this increasing or how much is this decreasing? Let's talk about the rate of increase. How much is this increasing? In other words, we want to first find the first derivative, which is going to be, if you notice this is the same as r over kv times 1, which is just the same thing, minus r over kv times e raised to minus kt. I want to realize that this and that is the same thing. And when we are taking the derivative of this is a constant, that is a constant, that is a constant. So this goes to 0 and we'll be left with that. So this is going to be the derivative with respect to t of minus r over kv times e raised to minus kt. So if you look into this thing here, this is a constant, this r, this is a constant, this is a constant, so we can pull it out of the derivative symbol here, and then we'll be left with the derivative, because the constant can always be pulled out of the derivative. And then here we'll end up having minus r over kv, and then inside here we'll end up realizing that here we have to end, if we're having e raised to t, we're just gonna say that this is the same as just e raised to t. But now we're not having that. We're having, instead of having a t, we have minus kt here. So because we're having that, we have to take the derivative of that. In other words, we'll end up having to multiply by minus k, and then of course this is a derivative of the exponent. We're using chain rule here. And then once you look into this will end up minus and a minus a positive, and then k and k, they cancel out, and you'll be left with r over v times e raised to minus kt as the first derivative, or the rate of increase. Okay, why are we saying the rate of increase? Is this an increasing function or is it a decreasing function? So if you look at this function here, this thing here is actually decreasing, so it's moving all the way, keeps going down. And of course we are separating from 1. If this one keeps reducing, so we keep separating small values and small values and small values, so this whole thing is actually increasing. So this one we are having its first derivative is actually the rate of increase. And then if you were looking at the other question whereby we had our concentration as d e raised to minus kt, then the first derivative of this was going to be the rate of decrease. So here, because this is an increasing function, the first derivative, it is a rate of increase. So we have the first derivative. Now this question is actually asking something which is specific. We wanted to maximize the rate of increase in concentration, so we wanted to maximize the first derivative. For the first derivative to be maximum, we wanted the second derivative with respect to time to be equal to 0. That is what is needed here. So what is important here is this: what is actually the second derivative with respect to time? You'll find out that the second derivative I'm gonna have to take the derivative with respect to time of r over v e raised to minus kt, and then of course this I'm gonna pull the constant out and then take the derivative with respect to time of e raised to minus kt. And then of course once you are there, you will find out that you are actually having an r over v, and then this one, the derivative of it is supposed to be e minus kt if this was only t, but it's not, so we have to multiply by the derivative of that exponent, which is just going to be minus k. So the derivative of that with respect to t, using chain rule of course. And if you take a note here, this is going to be minus k r over v times e raised to minus kt, and then this is actually the second derivative with respect to time. And then the next thing, because we wanted to maximize rate of increase. So we want to maximize the rate of increase. So this is actually what we want to maximize, the rate of increase. Now, once we are actually having this thing here, the next thing that we wanted to do here, we wanted to solve for t, right? We want to solve for t. So for this thing here that we're actually looking for here, we wanted to find out that this one here is going to be, remember that for the first derivative to be maximum or minimum, the second derivative with time is supposed to be equal to 0. So we want to solve for time. In other words, we want minus kr over v times e raised to minus kt is equal to 0. And if you look into this thing here, I can divide on both sides by this whole thing here. So I'm going to divide by minus kr over v, and then that side I'm going to divide by minus kr over v, because all of these are constants. And then if you look into this whole thing will cancel with that, and you'll be left with minus kt is equal to a 0, because 0 divided by any real number, you end up getting a 0. When is this thing gonna be 0? Remember that if we were to draw a Cartesian plane, this is going to keep it decreasing all the way. So this is only going to be 0 if t is actually infinity. So we actually will end up having this thing getting 0 if this one is actually infinite. In other words, this first derivative is going to be maximum when this one is actually going to infinity. So this one will be maximizing the rate. And now the second thing that I want us to talk about here is this. What is actually going to be the concentration at this t infinity? Remember that our concentration here is actually given by this. We have r over kv, and then we have 1 minus e raised to minus kt. And then of course, if you look into this one here, you will find out that when t is infinity, so at infinity, this concentration is going to be r divided by kv, and then we have 1 minus e raised to minus k times infinity. So that is what is going to happen. And then k times infinity, a constant times infinity, of course, is going to be the same as infinity. And then we have minus times infinity, that's negative infinity. And when you are having a negative exponent, that is actually the same as 1 over e raised to positive infinity. And then a positive constant raised to infinity is the same as just infinity. And then 1 over infinity, we know that 1 is so insignificant compared to infinity, is going to be a 0. And then this whole thing is going to end up being 1 minus 0 is just 1. 1 times this whole thing is going to be the same as that whole thing there. So that's how you end up getting this concentration at infinity. So once you are having this concentration here, bear in mind that this concentration must always be below the maximum concentration or maximum threshold. This is what the question is saying here. What infusion rate maximizes the rate of increase in concentration while staying below a safe threshold Cmax? So what we wanted to find here, we want to make sure that this one here is always less than or equal to Cmax. So below means less than. So we are having our R, and then we're having a K, and then we're having less than or equal to Cmax. So if I want to solve for R, I will just have R and then cross multiply. It must be less than or equal to Kv, and then we have our Cmax. So that is actually what we must actually have. So what infusion rate or what is R? That is what they were looking for. This question is not hard. You just have to realize something here, that the rate of increase, they're talking about the first derivative, and it's going to be max When is it going to be max? When its first derivative, which is the second derivative, is equal to 0. And this is only going to happen if this one t is infinity. And then if t is infinity, you know that you will end up getting that, and this is less than max. So that is actually what you end up doing in question number 15. So we are having this here. What t maximizes the rate of increases? So we must have that. So I can just say, as long as we have our r equal to that, we'll be fine. Let's go to number 15, and then we can call it a day. A pharmaceutical company wants to package pills in a cylindrical container. Each pill has a volume of this 0.4 centimeter cube. Remember that centimeter cube is the same as millimeters, so that's what is important. And the container must hold 100 pills. Question: what dimensions, radius of cylinder? So what is important here is that we want the radius and height. Okay, before I can give up and say this one is hard or this one is easy, and you think that this guy, he's lying because he has a PhD, that's why he's lying to us, this is not easy. I want you to realize something here. Wanted to package pill in a cylindrical container. A cylindrical container looks something like this, and then you will notice that this is actually not hard. It's just that I am not good at drawings. Okay, I'm going to just undo this, use this instead. A cylindrical container usually looks something like this. This is not that bad now. And then after that, it's supposed to look something like this. Looks something like this. And of course, you will end up having a radius here, and then you will end up having a height that is going somewhere there, and then you have a radius there. And then of course, because we cannot see this thing, this is just to show you that this has some height. So this one here is just a height. This one here is just a height, the same as that height, and this one is a radius. And when you look into this, you will always find out that the volume of the cylinder is always gonna be pi r squared h, and the surface area is always gonna be given by 2 pi r squared, 2 pi r squared plus 2 pi r. Why am I writing wrong things here? Pi r h. So that is what is happening here. And if you look into this one here, pi r squared is just the area of the top, and then this h is just the height. And then when it comes to this, the total surface area, you need the total surface area of this circle on the top, which is pi r squared, and also the total surface area of the bottom circle, which is also pi r squared. That is why we're having 2 pi r squared here, and then this part here is just for the body of this cylinder. So that is actually the cylinder and the information about the cylinder. So you wanted to put pills inside, and the volume of each pill is going to be 0.4 centimeter cube. That's what you want. And then the second thing here, you wanted to make sure that you have 100 of these things, 100 pills. So 100 pills, it means that the total volume of the pills, total volume of the pills is are going to be 100 times 0.4 centimeter cube, which is the same, I'm moving the comma 2 times, so it's going to be 40 centimeter cube. That is the total volume of the pills, because each pill is having that volume, so the total is going to be 100 times 0.4 times 100 is going to be 40. Yes, because these pills here, 100 of them need to be inside this cylinder, the total volume of this cylinder must also be the same and be 40 centimeter cube, because these pills needs to be inside here. So we have this equal to that. So basically we are actually end up having pi r squared h, pi r squared h is equal to 40, which means that our h is just equal to 40 divided by pi r squared. We are having the equation of the height. The second thing is here, what dimensions, in other words, we want to maximize what dimensions, radius and height of the cylinder cone, that will minimize the amount of packaging. So we want to make this thing as small as possible, so we want to minimize that. So if you look at the total surface area here, remember that we said that a total surface area is going to be 2 pi r squared and then plus 2 pi r h. And then if you are looking for the total surface area as a function of radius, it's going to be 2 pi r squared plus 2 pi r. Instead of h, I will have a 40, and then I divide by pi r squared. I'm just replacing this h here. And then after that, I know for a fact that this pi and this pi will cancel out. This r and one of these r's will cancel out. And of course, I will have 2 pi r squared plus 2 times 40. That's going to be 80 over r. And then the next thing that I want, because I want to minimize that, when this one is minimum, because this one is actually smooth everywhere except when r is equal to 0, which is not possible, because if the radius is actually 0, which means we don't have a container to hold any pill, so this one cannot be 0. So we know that the domain of this function here, our r must be bigger than 0, because that cannot happen. Now this one is going to be maximum when SR, the first derivative, is equal to 0. That's what we know. So basically, what is the first derivative of this thing? The first derivative of this is going to be this. We are taking it with respect to r, so we're only going to take the derivative of this. So we're going to bring in the 2, and then it's going to find this 2. So we'll have 4 pi r, and then of course we subtract a 1 and then plus, and then the derivative of this, remember that 80 over r is the same as 80 times r raised to minus 1, and then now taking the derivative of this, we bring down this minus 1, so we'll end up having minus 80, and then subtract a 1, so we'll end up having a minus 2 here. And then once you have a minus 2, it means that we are actually going to the denominator, so you have r squared. And if you look into this one here, you will find out that you are actually end up having I can multiply by r this nice thing here, and then end up having 4. Remember that this is the same as 4 pi r times 1, which is the same as r squared over r squared, and then minus 80 over r squared. Of course, r times r squared is going to be 4 pi r cube minus 80 all over r squared. The reason I'm doing that is because I wanted to end up multiplying by this. I wanted to end up having the common denominator, which is r squared. So this is my first derivative. Now, how do you find the maximum values of this? You want to find the absolute max. We want to find the minimum, so we want to find the absolute mean. How do you find the absolute mean? the first thing that you want to find out when you are looking for the absolute mean, you want to find out what is going to be the values of r. So set S prime of r equal to 0 and solve for r. So basically here, what is important is this. For this to be equal to 0, the numerator need to be equal to 0. So you have 4 pi r cube minus 8 is equal to 0. That's when this is going to happen. And then the next thing here, I'm going to divide by 4 pi throughout. So we'll end up having, or let me first take this to the other side. So we'll end up having 4 pi r cube is equal to 80. And then I divide by 4 pi on this side, divide by 4 pi that side, and then of course this will cancel with that, and then we'll have r cube is equal to, if you look into this one here, you will find out that how many 4s out of 80? We have 2, and then you come here and then you ask yourself how many 4s, you find out there's 0 of them, so you have a pi, and then you will end up having your r equal to the cube root of 20 over pi. So once you are having that as your r, the next question you should ask yourself is, you want to set the denominator equal to 0, or you set S prime of r undefined. Set it undefined and solve for r. So if you look for this one here, this is only going to be undefined if r squared is equal to 0. So if I have r squared is equal to 0, which implies that my r is just equal to 0. But r is equal to 0 is not in the domain of S. So no need to check it. If let's say r is equal to 0 was part of the domain of this function, we're going to check it, but now it is not, so there is no need for us to check it, like I said in the previous topics. So the next step now, I want to find what is going to be S of cube root of 20 over pi. So what is that? Remember, that is the only value that we have, so we don't have to even compare it. It is the value we're looking for. So we'll end up having, where's this nice equation, because I have to plug it in the original equation. Where's the original equation? Oh, this is the equation. So we have 2. I'm gonna shift, place a pi, and then I'm gonna end up having my r squared, which is the same as just the cube root of 20 divided by a whole pi, and then I want to, while I'm here, I want to square it, squared plus 80 divided by, I wanted to have a cube root, I have 820 divided by shift, I have a pi. So what is the answer here? So what I'm looking for here is actually a 64. So the absolute minimum is the absolute minimum surface area is 64.75 centimeter squared. So that is actually the absolute minimum with the dimensions my r is actually because this is the r that I have inside, so it's going to be the cube root of 20 over pi. And then actually the height now, because the height is actually defined in terms of r, so we'll have 40 divided by pi r squared. 40 divided by pi r squared, so we have 40 divided by pi r squared. But my r, we know that our r is the cube root of 20 over pi, and then we square it up. Of course, we can get a good approximation. So here I wanted to have a cube root of 20 divided by a whole pi, so this thing is going to be approximately 1.85 centimeters. And then this one here, and then I'm gonna have a 40 divide shift pi answer squared. We'll end up having 3.71 centimeters. So the height they were looking for in this question, if you look into this question here, you'll find out they wanted the radius and height to minimize the packaging or the surface area. So these are the height they were looking for and the radius they were looking for. I'm also gonna end up there. I am also tired. Hope you understood these questions. They are a little bit not straightforward when you're reading through them. Try and read and understand what each of these questions are actually saying, and write, just draw any graph that you actually you actually looking at, so that you can actually understand what is going on. And also another thing that I want you to be careful at here, which I introduced, these problems, when I was just doing them, I just noticed that I can just add even problem number 13. Hopefully problem number 13 will actually give you a chance to dig even further when it comes to operation research questions, some of these questions. And also you will also see some of these problems making sense, especially number 15, because when you are creating volumes, at least you know the pills, that each pill is actually of this volume. Then maybe if I'm looking for this number of pills, then I need a packaging material of this much. So these questions are some of the realistic questions you can actually see. And also another thing, if you're injecting certain doses, there are certain doses that need to be administered or managed in a careful manner. In other words, if let's say you know that once there is an overdose of this, some patients might not actually react well if we are exceeding this amount of concentration. So you want to make sure that you don't make that mistakes, especially if you are doing pharmacy. Don't make that mistake, because that is one of the things most people usually do. So this is actually the last part of us, amongst us, that is focusing on derivatives. Next, we'll actually look at how we can actually deal with areas, because now we're dealing with the slopes, the slope of the curve, or the slope, or the slope of the tangent line touching the curve at a point, and we talked about that as a derivative, and we saw that derivative can actually work, give us a nice understanding of minimization problems and also optimization problems. So those are the things that are actually much more important that you need to actually be more familiar with. So now we'll look at the area and see how can we talk more about area, and how can we find the area under the curve, or the area between the curve and the x-axis. Of course, because of our syllabus, we usually look at things that are much more suitable for our fields. We're not gonna go into deep questions such as find the area between this curve and that curve. We're not gonna do that, but hopefully you will get something. I'm gonna stop there, and then yeah, I think that's it.